Are live once again. One of these episodes. I think we probably settled on the name. Maybe.
I, I think so.
What are we gonna call this thing?
The uncertainty principle,
The
which
uncertainty
is a
principle.
which is a nod to Werner Heisenberg.
Heisenberg.
Yeah.
Explain what the uncertainty principle is. Do you know it?
Basically, you can't know the momentum of a particle and its precise precision at the same time.
Yeah, you can't know where things are at and measure its momentum at the exact same time because one affects the other essentially, right?
Correct.
Yeah. Um, which is a pretty weird physics conversation that maybe we'll have at some point. But I think that kind of the name itself, anyways, describes what we're doing here. Is just we're mostly uncertain about the things we say,
Mhm.
seeking to learn more and understand science a little bit more and the stuff that's around us. Um, so yeah, that's what myself, Edgar, is doing. And who are you?
I'm Richard Fletcher. YouTube moniker, engineer of reality, which that'll mean something one day, maybe.
Yeah, we're just trying to figure this out. We like to talk about science stuff. I'll update the logo and we'll probably get a website and a dedicated YouTube channel for this thing. Um, now that we've kind of figured out what we're gonna call this, yeah, this is gonna be good.
Yeah, yeah.
Um, one of the things that I like to do is every time that we talk about something that is real, that is a fact, because so far I think we've two or three episodes we've dedicated to things that are just hypothetical thing,
Hypothetical.
not a fact, not in any. So there's no fact checking on stuff that's not proven because
Right.
it's kind of difficult to say let's fact check something that is not proven. But
Mhm.
I do like to fact check stuff. Last week we talked about
The Casimir effect.
the Casimir effect, and one of the things that I did probably incorrectly was trying to. There were just analogies more than anything else. So I don't feel too bad on the way I spoke about them, but it still deserves clarification, and that is giving analogies and comparisons or yeah, I guess that's the best way to say it from something that is here on Earth and
Mhm.
something that's in a vacuum. So I gave the analogy of the balloon in a bottle and how if it doesn't have a hole, it'll deflate, but if it does have a hole, it'll deflate up at the top. So like if I have this bottle and I have the balloon on this end right here, and I put it in there and I blow up the balloon inside the bottle. If I have a hole on this side, but that hole is not covered, I uncover it, it'll deflate because of the pressure. But if I blow up the balloon and I plug the hole, the balloon will stay the way it is because it basically pushed out all of the air and there's no pressure to deflate the balloon. So that was one of the analogies that I was giving, but obviously that's not a perfect comparison. It's not the same thing. It was just kind of a early thought process that I was having in my head. One happens
Mhm.
in a vacuum, the other one doesn't happen in a vacuum. So obviously that alone is going to make things vastly different, right? One is requires pressure, air pressure, and the
Mhm.
other one is the absence of that. So it's not the same. I think the other thing we talked about is photons being charged, which is we alluded to it. We didn't say this is the way it is. This is exactly it. It was kind of brought up, and obviously that's not the way it is. Photons are not charged. The object's plates are kept uncharged, So electrostatic forces do not swamp the much smaller Casimir force. So I
Yeah.
think we kind of said that. And then the other one,
I think the train analogy for me. So
oh yeah, go for it.
yeah. So I mean, with the train analogy, really, it's the speed of the air between the train versus the speed of the air on the outside of the two trains that would draw them together. As they get closer, as they start to travel the same speeds, the speed on the inside, because they're, well, it's similar to the Casimir effect, but the what's happening is the air that's on the inside of the two trains, um, it starts to run out of space in order to displace the two trains apart, and so they start to attract each other, or it basically speeds up enough to where the particles don't last on the inside of the train more so than the outside.
Yeah. And again, and I think this is the tough thing about having these conversations. You give analogies and you give like it's similar to so that people can understand it a little bit better. I know in many times it's helped me understand it, but it's also in the small amount of time that we have with humans on this podcast, it's sometimes difficult to convey that message. Like this is just a very low level example. It's not identical. It's not um but there's nothing else to compare it to. Like we're trying to get you to understand kind of how it works, but it's not exactly how it works, and it's tough. It's tough. I think you said one similar to, or I said one, I don't remember. We talked about tornadoes and
Mhm.
um removing pressure from the metals, which again, it the same conclusion to this fact checking segment or section of the show, and that's it can't be the same. The Casimir effect happens in a vacuum. Tornadoes, from what I understand, cannot happen in a vacuum. I think that kind of be the opposite because they require difference in pressures, atmospheric and air pressures. So
Yep.
Casimir effect happens in a vacuum. All of the analogies we gave were here on Earth, essentially. So there were just examples, maybe bad analogies, but analogies nonetheless. So either,
Just to try to give a visual representation of what's happening, but not why it's happening.
yeah. But I think it's still important to kind of clarify that and not I and not that we're doing this, but not disrespect to the science, not minimize the science, I guess if that makes sense. So anyways, for me it's always important to clarify or correct any mistakes that we've made on previous episodes. Um last episode we also I heard of a new principle, and that is how do you what do you call it?
Um,
The
shoot,
Coulomb's law?
Coulomb's law. Yeah.
I wonder how you say it. Coulombs or B, I'm sorry. Coulomb's law.
Yep.
What is it?
It's basically a law of electromagnetism. So it's kind of an experimental law. Calculates the amount of force between two electrically charged particles.
Okay. So
So,
here's what the AI machine says on the Googles.
mhm,
So take it for what it's worth. I always encourage you guys to go look this up. Um, it does give references, but it sometimes, a lot of times, it pulls shit from like Reddit, and that's not a good resource. Reddit, although rarely, sometimes it does have good information. Rarely, but overall, Reddit is a cesspool of fucking information. So I don't encourage you guys to really pay attention to that too much. But at any rate, this is what it says here. Coulomb's law. or electrostatic force is the attractive or repulsive force between two charged particles calculated, and then it gives you the equation. It is directly proportional to the magnitude of the charges Q1, Q2, and inversely proportional to the square of the distance between them. The force acts along a straight line line joining the charges with opposite charges, attracting like charges and like charges repelling. Is this just North Pole and South Pole? Is that
It's similar. It's the relationship between the nucleus and the electrons, the outer electrons. So, yeah, it ties into atomic physics. It describes electrostatic force of attraction between the positively charged nucleus and negatively charged electrons, which determines the atomic structure of a particle.
all right? We're gonna have to slow this shit down for me because I got lost. So
Okay.
F equals K. All right. So one force. So if you're looking at the image, oh, I need to share the image. Hold on. I just
Oh,
noticed I'm not sharing the actual image.
so I'll
Uh,
start off by saying that everything you touch is lying to you. It goes back to electrostatic repulsion, or electromagnetic repulsion.
here we go.
Not actually touching anything. Your hand never truly contacts your table, and what you're feeling is electromagnetic repulsion,
But
which is
is
basically that, huh?
is it the same thing? Like
It, it,
I know we talked about that in a previous episode where we talked about electromagnetic repulsion and the weird thing that we don't technically touch anything. So like I get that,
mhm.
but
So yeah, they're basically atoms pushing back before they meet. But then, um, this the Coulomb's law comes in, when it comes to things like your static cling, your shirt clinging to you fresh out of the dryer, sparks jumping from your finger to a doorknob.
there is an
Um,
attraction, but there's also an attraction.
yeah,
So Q1, Q2, and inversely proportional to the square distance between them, the force acts along a straight line, joining the charges, so bringing the charges together, with opposite charges attracting and like charges repelling.
yeah.
So
We talked
opposite,
about we talked about when the electrons are spinning in the same direction. That'll be a like charge, so they repel, and that's what you feel when you touch a solid object.
yeah. So here in this image we have F12. So that's Q1 and then Q2. They're positive, so they repel each other.
Hmm.
And then down below it is F12, F21, but Q1 positive, Q2 negative, and they're attracting each other.
So if I break down the equation itself, F actually is how hard things push and pull. That's your force,
That's the force. That's the vector form.
right?
Hold
Uh,
on. Let me go back to just so that people follow along to what we're looking at here. It's just so we understand the equation a little bit more. Okay, go ahead. So the formula is F equals K,
mhm,
Q1, Q2 over distance squared. Um,
correct. Yeah. So R2 would be R squared is your distance, and that's what kills your force really quickly. So your force is how hard things push or pull. Q1 and Q2 is basically how charged the objects are.
yeah, charge one, charge two.
Yep.
Uh, D is
K is
distance, or
Yeah, K is just a scaling constant. So that's all it is.
yeah, that's just the. Oh, this image is moving for those of you guys that are actually watching this and not just listening to it. You can see the image kind of moving right now. Hopefully, you can see it. So the vector form. F12 equals K, which is the constant, Q1, Q2, distance squared, represents the force vector on Q2 from Q1, where the distance is 12. Yeah, I'm not even going to pretend. This is why I didn't go into fucking physics. All of this shit right here is just like, I don't know what the fuck you're talking about. Like, I'm sure it's easy to figure it out.
I was forced to take a couple classes, but that's about it.
Yeah, this is. Let's see if we can find something else that breaks this down. Everything's going to say pretty much the same thing. Um, I want to find any experiments. Experiments.
So to kind of make it
Oh, go ahead.
stand out and make it visual, basically, if you double your charge, you double the force. You double the distance, the force drops to a quarter.
Hmm.
And then opposites attract and the same repels. That's pretty much it.
Okay. So the Coulomb's law experiment demonstrates the electrostatic, but what is the experiment? Torsion balance, a delicate balance beam suspended by a fiber with a small charge pith ball on one end and a counterweight on the other. Charged objects, two small conducting spheres, pith balls, are used to store charge. Measurement tools, a scale to measure the angle of twist, torsion, and a ruler to measure the distance between the spheres. Um, oh, okay. So this is not just a hypothesis. This is much more than that. We got a lot of one main experiment that proves what it does.
Correct.
That's crazy.
Now, where it actually shows up is in things like static shock, which is just electrons jumping gaps.
Yeah.
That's it. Lightning, same thing, but at an insane level.
Yeah, that's a lot of force.
Yeah.
It's a lot of
So,
force.
so electrons orbit the nuclei of atoms just because of that force. So that's what we're trying to look at, or that's what Coulomb's law is measuring.
So the electrons, let's see, let's look at an atom. Let's get you an atom. Doo-doo-doo. Let me share this really quick, and
Hmm.
then that way the homie Richard can. All right, so I've got a. We've got a model right here, and there we go. So the black, if you're watching this, oh, I need to change this again. Need to share the new picture. Sorry. There we go. Model of an atom. So you got the nucleus. The electrons are in black. The protons and the neutrons are always obviously part of the nucleus. They're in the middle, represented by green and red. And then you've got the shells. You've got the shells, which I'm imagining are the lines. So the electrons are orbiting the nucleus.
Yeah.
And then
And it's the force of those electrons orbiting the nucleus is what Coulomb's law is measuring.
and if you've got another one that has the same amount that are positively charged, they will repel each other.
Right.
And if they are opposites, they will attract each other.
Right.
How is this not? All right, I'm going to take this shit off and I'm just going to look something up really quick because now my brain is like, how is this not just magnets? Um,
We haven't figured out how they work yet.
let me see. Sorry for the dead space. But
So
go ahead. Go ahead.
we can look at different contrast forces like electromagnetic force and gravity. Um, Electromagnetic force is stronger than gravity. It's about 10 to the 36 power times stronger than gravity.
But gravity's different.
Gravity's different. It's a different type of force.
If you want to call it a force, I would disagree that it's a force. Um,
Yeah,
I think math would disagree that it's a force because because gravity is the curvature of space time. That's
correct.
what gravity is. So it just you're going in a straight line. And let's pretend I'm light. I'm going in a straight line, but there's a big fucking sun in my way,
Mhm.
and as I'm going near it, I end up bending around it because the space that I'm traveling in, the line that I'm traveling in, is being bent by its mass. This is different. This is electromagnetic static or just electricity. So Coulomb's law, electrostatics, and magnetic force laws are mathematically similar, both following an inverse square relationship, but they are not the same thing.
Mhm.
Got Coulomb's law describes forces between stationary electric charges, while magnetism involves moving charges, currents, or magnetic poles. They are related as components of electromagnetic magnetism, not identical. Again, that's from Reddit though, so fucking be careful with that shit. Um, but they're not the same. So, and the biggest thing right here would be again. Let me see.
I will say this on Earth: if gravity disappeared, you'd probably float. But if magnetism disappeared, you probably wouldn't exist
M-
because that's what makes the structure of atoms. So
If electromagnetism didn't exist, we wouldn't exist
correct.
because atoms rely on it.
Yeah, that's what makes their structure.
Yeah, I have nothing for that. I, I don't know enough about electricity.
Mhm.
In terms of science, that's probably my weakest point is electricity. I
Um,
would say out of all of the sciences, I think it's fair to say. See, now just pulling that. I mean, yeah, electricity is probably not my weakest one. Not from Reddit.
mhm.
Oh, it's just gonna pull up Reddit now.
It's because you thought it.
Yeah, I thought it. So now it's just gonna pull up Reddit. I fucking hate Reddit as a source. So let's look at Wikipedia. Not that Wikipedia is any better. Coulomb's inverse square law, or simply Coulomb's law is an experimental law. Nope, that's just giving you the
I think
versus.
it says something in Wikipedia about how it's very similar to Isaac Newton's, uh, or it's related.
All right, here we got another one that's not Reddit. Coulomb's law, electrostatics, and magnetism force law both describes the inverse square forces proportional to the charge, electric versus magnetic pole strength. The primary differences are that Coulomb's law deals with static charges, while magnetism applies to dipole poles, and uh, magnetic poles do not exist, unlike electric charges. Fundamental nature, Coulomb's law, F equals Q1, Q2 over distance square involves static electric charges. Magnetic force involves north-south poles, often formulated in Coulomb's law of magnetic force, although magnetic monopoles rarely exist. Monopoles versus dipoles. Electric charges can be isolated. Monopoles. Magnetic poles cannot. Breaking a magnet simply creates smaller dipoles, north and south pairs. Huh, I didn't know that.
Mhm.
Force behaviors. Like charges repel, opposite attract. Similarly, like poles repel. So very similar, just not the same. That's fucking weird. That is so weird. I guess that's
Yeah,
basically like me being Mexican and then I find a Puerto Rican. Like it's basically the same thing, but it's not the same thing. Um
yeah,
that's weird. Because
mm,
it's almost all the same. Like it's the inverse laws are the same. The way the forces are the same. Same shit. Repel, opposites attract. Almost everything's the same except one deals with magnetism, the other one with electrostatics.
yeah. Which you need two poles for each one, but something about, well, electrostatics. If you break a pole, it's gone. There's nothing for it to jump to.
Electric and no, but electric charges can be isolated, monopoles. So that's Coulomb's law, monopoles. Magnetic poles cannot. So dipoles, which is magnets, you cannot break them apart. But in
Mm,
Coulomb's law, which is all electrostatics, you can break them apart. You can isolate the poles.
right.
In magnets, you cannot. Interesting. And then it would, if I understand this correctly, Coulomb's law is static, not like static as in hair static. It's static as in it doesn't move, if I understand
Mhm.
this correctly.
Yeah,
And magnetism is flowing.
yeah. It's movement
Yeah.
of force.
I don't know. I'm gonna have to call Coulomb right now and see what the fuck he's talking about.
Is he around?
I don't know. I don't know. Is he around? Let me see. Who came up with this batshit crazy thing? Oh no, he's. Uh, I'm gonna show you his picture from Wikipedia, and I'm gonna go out on a limb and say this fucker is long gone.
Is that George Washington? Wait,
No, that's Charles Augustine de Coulomb.
yeah,
Um, so that dude's dead, dead.
18th century, I think, is where he's from.
No, 17. Born 14 June 1736, died 23 August 1806 at the age of 70.
Oh,
Uh,
oh,
yeah,
he lived a long time in that time.
yeah, yeah. He was fucking 70,
Yeah.
70 years of age. Yeah, this is another one of those where I just don't understand enough. I'm telling you, anything that has to do with electricity, my brain's just like I get I understand it enough to know that it works, and if something were to break here in my house, I can mostly fix it. Um, but like this stuff right here is just weird, man. Just weird.
Yeah. So it's basically the reason that electronics need grounding. So that would be, you creating a dipole, I mean, a
Monopole?
monopole system for electrons to move through.
Yeah.
So if you were to break that, or you break that contact, they're not moving anymore.
Okay. Again, I'm using my brain, which knows very little about electricity. My understanding of the grounding in my electrical panel is so that the quote unquote overcharging, I don't know if that would be the proper term. There's too much load, has somewhere else to go
Mhm.
instead of inside of the house. So like Now in 2026, in modern homes, if they're done correctly, I don't have to worry about lightning hitting my house and it blowing up my TV like we once used to worry about, because this was a lot of stuff that I heard from old people when I was growing up is if there's lightning, turn off the electricity. So like that was a thing at some people's homes, is turn off all of the electronics. But now in 2026, I don't have to worry about turning off, because if we get hit by lightning, my house is grounded, and that extra energy goes into the ground. It leaves. It doesn't come inside the house. My shit's not gonna blow up. Not likely. Not likely to blow up.
Right.
So
Yeah.
how did go
I
ahead.
blew
So
up a
how did
router.
what
My
what
pond in the backyard got struck by lightning and blew up a router that was sitting at the nearby the door.
oh, it wasn't grounded then.
Probably didn't have the best ground in this house, but yeah.
But nothing else blew up.
Nope, just the router.
Just the Ethernet router.
Hmm.
Yeah.
Which was connected to nothing that had to do with the pond, but yeah, it stopped working.
That's crazy.
Hmm.
Or maybe just the charge around it got the box all by itself.
Could be.
Yeah. Because I know for a while during lightning storms. I mean, you've seen this in I've never seen it in person, but I know what it means. If you're somewhere and your hair, you and I don't have this problem, so we'd be fucked. We wouldn't know how this happens, but
Right.
you could watch videos of people, their hair frizzes up, and a lot of them are like, "Oh, this is cool," and then those of us that know that like you're about to die, uh,
Hmm.
that means that the electricity is starting to build up, getting close to lightning striking near you.
Yeah.
Uh, so
That's
there's
why
all of
I try to hang around people that have hair so that
yeah,
I
yeah, yeah, yeah.
can see.
Have a very hairy person,
Yeah.
so you know when lightning's gonna strike.
Right.
All right, so I want to go back to the grounding shit because I want you to explain to me how Coulomb's law affects grounding in your house, because I don't fucking get it.
Um, well, the only thing that I can explain is the movement um of positive electrons from positive to a negative source. That's the basis of grounding. And so Coulomb's law is, you're not breaking that monopole. Basically, the movement of those positive electrons to its negative source. Um, that's the only reason for grounding. Now in a house, it may it's ground protection in a house, but for most devices, say your car, that's running on DC voltage, it
Yeah.
needs a positive and a negative system in order to run.
All right, so I did the Googles. Google says yes, Coulomb's law is fundamentally why grounding is needed. It defines the forces between charges, showing that opposite charges strongly attract, while Coulomb's law causes like charges to repel, leading to dangerous imbalances. Grounding provides a safe path for excess unwanted charges to disperse into the earth. A neutral vast reserve, this that's in parentheses, a neutral reservoir, reducing their Coulomb force interaction with equipment or people. Balancing charges. So we already talked about the equation, safety path. Without a ground, electro electrical devices can accumulate charge, creating high voltage differences that can cause electrostatic discharge. The ground's role by connecting a conductor to the earth, excess electrons are attracted to the massive charge reservoir, neutralizing the system through Coulomb's force acting over a distance. Why grounding matters. Lightning protection diverts massive charges accumulation to the ground, as described by five. We should be looking at something, I think, from Boston University. System stability prevents charges from destroying sensitive electronics or harming users by using the ground as neutral potential reference. Got it. Got it. So, because you would have too much of the same energy and they would want to repel each other because it's the same. They're not opposite,
Same
they're the same. And,
electrostatic charge, then it'll be looking for something that's the opposite. So
and
then
that's
you
what
come
it's,
along and you touch it.
yeah. Yeah. And we make really good ground conductors.
Yeah,
Uh, we tend to attract electricity very well. To your
especially
point,
especially if you're standing in a puddle, it's even worse.
if you're in water,
Yep.
because the
All you have to do
water,
is stand in one puddle and your body's resistance goes down
and you keep it, it doesn't go into the ground because the water's acting
as an
as a
insulator.
barrier,
Yep,
as an insulator. So the electricity stays inside of you instead of passing through you.
correct.
Is that what you're saying? Yeah. So more likely for you to die. I mean, you're probably fucked either way if you get hit struck by lightning.
Yep.
My uncle he was an electrician and he got zapped a few times, but one time by lightning. And really the only thing that helped him out was that the electricity went through him and it did not get stuck in him. So
Mhm.
it went to the ground. It wasn't a direct hit. It was kind of by the side, and some of it zapped through him and
Uh,
then into the ground. Yeah, that's interesting.
so we're concluding that here that the solid world isn't solid. It's made of electrons.
You're concluding that. You're concluding that. I'm not concluding this.
These atoms, they're made of electrons. Either they're spinning positively or they're spinning negatively, and that creates that structure of the atom. And then you compress those together, and now you have solids. You have electrostatic repulsion, which is your solid mass. The force of the charge, your body interprets it as a harder substance or a harder surface.
You said electrostatic
Repulsion.
repulsion is mass. I'm gonna I'm gonna ask the interwebs. No, electrostatic repulsion is not the same thing as mass. Electrostatic
No,
repulsion.
I'm not saying it's mass. I'm saying that the electrostatic repulsion, the amount of the charge, your body interprets it as the the how solid the object is.
Got it.
So,
Electrostatic repulsion is a force acting between two charges of the same sign, while mass is a fundamental measure of the amount of matter and inertia in an object. They are, yeah, I get what you're saying because we did talk about the plenty of studies that exist that make you feel the mass.
mhm,
This microphone has mass, but the electrostatic repulsion is what I interpret as feel, but it's a repulsion. Yeah, yeah,
yeah,
yeah. I get what you're saying.
fields pushing against fields.
Yeah, for sure. All right. I don't know how much more I could get out of this one, uh, unless you have
Um, you can always compare Newton's law. Remember, I was
which
telling you
one?
about Newton's law of universal gravitation. So that's very similar to this.
Oh, the original new gravity,
Yeah.
OG gravity. Yeah, but yeah, I get what you're saying. If we go to OG gravity, we did used to believe that gravity was a force, and until Einstein was like, nah. this dude doesn't know shit. But the math still does apply. I mean, we can still use math. Shit, math. Newton's math is what we use to get to the moon. Artemis still used that. The Apollo project still used that. They used Newton laws. They didn't use Einstein laws,
Yeah.
or equations. I'm sorry, not laws. They still used Einstein laws, or that physics, but they used Newton's equations to get us to the moon. Yeah, 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 for
Mm.
sure. Um,
Yeah, Coulomb's law is basically the same thing, but without mass included because it just has to do with electricity, static.
are you sure? Are you
I
fucking
think so.
lying to me?
Newton's law has mass. It's this formula is very similar, but it's using the gravitational force. I mean, not gravitational force. It's using charged objects or charged electrons rather than mass.
All right. Coulomb's law and Newton's law of gravitation are both fundamental inverse squared laws describe forces between objects, electric charges, and always attractive, while electric forces can attract and repel. So mathematically, they're about the same, but one's dealing with charges, the other one's dealing with mass. Yes.
And if you want to go really deep into this, you
Again,
can,
gravity is attractive. Magnetism is both attract and repel.
yeah. If you wanted to even dive deeper into this, you can do quantum electrodynamics or QED. I think me and you discussed this one time
Uh-huh.
on one of the posts that I'd put up. Um, yeah, that would be something else. That'll be something for a future show.
Well, which we can talk about that. There's one, and I'd have to check this out, but there is a claim that almost everything we talk about is essentially
Electronics.
what's that?
Electronics.
No, mm-mm. I know you love electronics, but um,
Kind of surrounded by it.
kind of. But we're surrounded by all kinds of other shit too. Um, Newton's second law. So I'm wondering if all of this just ends up going back to Newton's second law.
Hmm.
Uh, I'd have to. I'm gonna show that to you. But Veritasium did this video, and where he talked about that no matter what you're looking at, almost everything comes back to this. Now I don't I say almost everything because I have to be careful with absolutes, and I'd have to rewatch that video again. But every conversation you go to essentially just translates back to this Newton's second law.
Yeah.
Um, almost everything is so that'd be interesting to kind of dive into and but I'll share that with you. I'll share that video with you so you can study it and we can talk about it. But QED sounds interesting as well. Um, for sure, for sure, for sure.
It's the future.
Maybe, maybe I'm I'm always careful with designating something as this is the way it is and this is the way it will be.
Hmm.
We've said that about so much, and almost every time we say this is the future, it never pans out that way. AI, flying cars, kitchen of the future, politics, almost everything is not.
Fiber optics. There you go.
Fiber optics. Yeah, we've always I think we've always accepted that is a better medium to send information. Um, for sure. Lights, all of that stuff. Yeah,
Hmm.
I don't disagree with that. I don't know if it's
It's just really, really advanced Morse code. Just letting you know.
I mean, it all is though, because I mean, binary code. That's all it is. It's just a form of Morse code,
Mm.
except with zeros and ones. Um, so yeah, I don't disagree there. Don't disagree there at all. But all right, I
Yep.
think I've squeezed out as much as I can squeeze out of Coulomb's Coulomb's law. He's French, so Coulomb.
No, like
Uh,
Colombia, but
Col-
not quite.
Coulomb's law.
There's an extra U in there.
Yeah, yeah. It's a weird name. Um, you have anything else to say about all this shit?
No, I just know that I have to go to bed every Tuesday with my brain just like completely active. This
It's
is terrible.
it's so weird because I have a difficult time anyways going to sleep. It's been getting better. It legit has been getting better with walks and doing stuff and not being a lazy fuck. It's definitely gotten better.
Mhm.
Or maybe the depression is just that bad right now that it's just fucking Um, but it is tough to have these conversations because now all I think about is like, what else can we talk about? What about this? What about that? Which, by the way, I've always been interested in this stuff. So I've always had these 2 a.m. Let me look up what this is and let me look up what this is. And so I've always been interested in the science stuff. But yeah, you're right. After Tuesdays, we're like, "Ah, shit, I should have said this," or "What about this?" or "What about that?" So, like, it's just this peak of intrigue, for sure, so
So then I spend the rest of the week just writing articles and reading stuff, and that's where I get a lot of the information that I put on my Facebook. So
yeah, yeah, yeah. So, alright, dude.
yeah,
Um, I appreciate the handful of you guys that tuned in. Hopefully in the future, we get comments on this one, corrections, and just additional information about this stuff, your information about it. But I appreciate you guys tuning in. Again, at some point, we'll probably make a separate channel, and maybe I'll have it by next week. And that way we can post up a lot of stuff. Maybe have a website, a blog style website, where we can post up the podcast and also the articles or anything like that we might have. So
yep.
appreciate you guys. Thanks for tuning in. Thanks for entertaining us and tolerating us. We'll see you guys next week.
All right.